Imagine you're just standing there. The ground feels totally solid, right? But then, a low, terrifying rumble echoes from deep down, zero warning. The earth literally groans, and the ground violently heaves, throwing you completely off balance. Buildings are swaying like they're just fragile little trees in a hurricane. Suddenly, the very foundation of human civilization feels, well, agonizingly thin. Welcome to this explainer. Today, we're diving deep into the science, the raw, unstoppable power, and the profound mystery of the unseen beast right beneath our feet, earthquakes. So, how do you even begin to explain the sudden, inexplicable destruction of your entire world? For thousands of years, the cataclysmic arrival of an earthquake completely defied all logic, leaving our ancestors in sheer terror. Take ancient Japanese mythology, for example. Their answer was Namazu. Namazu is this giant mythical underground catfish that supposedly carried the islands of Japan on its back. The story goes that a demigod had to hold this massive, heavy stone over the beast just to keep it still. But if that demigod's attention slipped for even a second, Namazu would thrash and the earth would violently tremble. It's this beautiful, kind of haunting story born out of pure desperation to understand. But honestly, the actual scientific reality of what's happening right beneath us is even more staggering. All right, Section 1, Awakening the Giant Catfish. Let's move from myth to mechanics.
Okay, so our Earth isn't just one giant solid sphere. Actually, the Earth's crust and the upper mantle make up this really thin, fragile skin that's broken into massive, shifting puzzle pieces. We call these tectonic plates, and these colossal fragments of rock are constantly on the move, just creeping along in the dark at roughly the same speed your fingernails grow. Pretty crazy, right? But here's the catch. Their edges are incredibly rough and jagged. Because of this massive friction, while the main bodies of these plates just want to keep drifting, those jagged edges lock together. And that's when this immense, invisible, and frankly terrifying tension starts building up deep underground. And we're talking tension that builds for decades, or even centuries.
Which brings us to Section 2, the breaking point.
To really understand this breaking point, we've got to look back at the absolutely devastating 1906 San Francisco earthquake. Picture a scientist named Harry Fielding Reid standing in the smoldering ruins of the city, acting almost like a detective trying to uncover a massive planetary secret. After looking at these incredible ground displacements, Reid realized something totally profound. He concluded that an earthquake isn't the cause of a surface rupture, but rather the result of one. It's called the elastic rebound theory. Basically, the Earth acts like a giant geological elastic band. It painfully deforms and stores up elastic strain energy over time, right? Until the rocks simply cannot hold on any longer.
You can actually see the silent progression of this tension perfectly right here. Look at time 1. The fault is completely locked up. Nothing is moving. But by time 2, decades of relentless tectonic motion from further away have forced the surrounding rock in that locked region to take on immense elastic deformation. They are literally agonizingly stretching and bending over years. And then, time 3. The absolute limit is reached. In mere seconds, the rocks snap, and they spring violently back to their original, undeformed shape with completely devastating force.
This unimaginable force unfolds in 3 incredibly rapid stages. Step 1 is that silent, centuries-long buildup of accumulated strain we just talked about. Then comes Step 2. The exact fraction of a second the rock's internal strength finally gives out, completely overwhelmed by that immense tectonic pressure. And then Step 3, the sudden, violent rupture. The Earth literally snaps. Energy stored for lifetimes is released almost instantaneously. Part of it erupts as scorching heat, part of it just shatters the surrounding rock, but primarily it's released as elastic waves. Those are the violent vibrations that rip through to the surface and cause all the chaos.
So, Section 3, Fault Lines and Fractures. Let's look at where the Earth actually snaps. These deep geological scars are classified by exactly how the Earth fractures and moves. First, you have normal faults. These happen when the crust is being painfully stretched apart, which drops one massive block of rock downward. Then you have reverse or thrust faults. This is when the crust is compressed, violently pushing one block upward. Fun fact, this is the exact sheer, unstoppable force that built the mighty Himalayas. Next up are strike-slip faults, which involve horizontal shearing. Think massive blocks relentlessly tearing past one another side to side, just like the infamous San Andreas Fault out in California. And finally, oblique slip faults. These are just a chaotic, destructive mix of both vertical and horizontal movement, a real geological mess. Moving on to Section 4, the anatomy of a tremor. Let's talk about the waves themselves.
When a rupture finally happens at the hypocenter deep underground, it fires off two distinct types of body waves. First out of the gate are the P waves, or primary waves. They are the absolute fastest. They compress and expand the material they travel through, kind of like a sudden pulse rushing through a slinky. And they can rip through anything, solids, liquids, even gases. Following right behind them are the S waves, or secondary waves. They're a bit slower, but they violently shear the rock side to side or up and down. Now here's where it gets absolutely fascinating. S waves can only move through solid rock. When scientists realized these S waves were completely vanishing at a certain depth inside the Earth, it led to a staggering discovery. It was literal proof that the Earth's outer core is an ocean of molten liquid. How cool is that?
There's a quote that brilliantly illustrates how we actually experience an earthquake up at the surface. P waves are like the lightning flash, and S waves are the thunder that follows. A seismograph detects those incredibly fast P waves first. If you've ever felt a mild, sudden jolt, that's the P wave. It's the flash of lightning. But moments later, the thunder rolls in. Those slower, highly destructive S waves arrive, and those are what tear cities apart. And get this, that terrifying time delay between the lightning and the thunder, that's exactly how scientists calculate just how far away the unseen beast awoke. Okay, prepare for a bit of a plot twist. Section 5. When humans shake the Earth.
Magnitude 5.8. That is the devastating size of an earthquake that struck near Pawnee, Oklahoma back in 2016. It was so massive people felt it all the way in Arizona. But here is the really shocking reality. It wasn't a natural tectonic event. Nope, it was induced by human activity. Specifically, it was caused by years of injecting high-saline wastewater from the oil and gas industry deep into porous rock formations. Pumping in this immense volume of fluid dramatically increased the subsurface pore pressure. Basically, we accidentally lubricated deeply buried ancient faults until they violently and uncontrollably slipped.
It turns out the more we dig, drill, and build, the more we actively alter the crust's super fragile stress state. We've induced earthquakes through deep wastewater disposal, sure, but we've also caused them by building massive artificial lakes. The sheer, unfathomable weight of the water at the 1967 Koyna Dam in India actually triggered a 6.3 magnitude quake, a horrific tragedy that cost over 170 lives. We trigger them through mining, fracking, and even geothermal energy extraction, which caused a devastating 5.5 magnitude event in South Korea. Even underground nuclear testing has been proven to aggressively release stored-up tectonic strain. We are literally waking the beast ourselves.
To try and manage this self-inflicted danger, regulators rely on something called a traffic light system. It's this tense, real-time monitoring protocol designed to basically keep the Earth asleep. If local seismic activity stays low, you get a green light to operate as planned. If minor tremors start registering, the light turns yellow, meaning operators have to immediately modify or lower their fluid injection rates. And if the magnitude hits a critical threshold, flashing red light, immediate shutdown of all operations. But honestly, even with these desperate safeguards in place, it is incredibly difficult to stop delayed seismic reactions once millions of gallons of fluid are already sitting miles deep underground.
Moving along to Section 6, Echoes of the Deep. Let's look at the chain reactions. You know, earthquakes don't just happen in a vacuum. They are deeply and terrifyingly interconnected with other volatile systems on our planet, especially volcanoes. A massive earthquake can fundamentally alter the stress field around a volcano. It can tear open hidden new pathways for magma to rise, or completely destabilize a pressurized magma chamber. Sometimes, just the seismic waves traveling from a distant quake can agitate a magma body. It's literally like violently shaking up a pressurized bottle of soda. If the system is already at a critical point, those waves can trigger a catastrophic eruption. It's just a breathtaking, scary display of how interconnected the Earth's power really is. But here's the ultimate unpredictability. Despite all our incredible scientific advancements, despite mapping out all these hidden fault lines, constantly monitoring those subtle P and S waves, and mathematically calculating elastic rebound, we still face a profoundly humbling reality. We know where earthquakes are likely to strike. We can forecast long-term hazard risks and painstakingly engineer our cities to withstand the shaking. But predicting exactly when an earthquake will strike, that remains a complete scientific impossibility. The unseen beast moves entirely on its own deep geological clock, and it is completely indifferent to human time.
Which leaves us with this final lingering thought. We are living on the thin, fragile skin of a violently dynamic planet. We're out here boldly charting its depths, building massive dams, and forcefully injecting fluids deep into its fractures. As humanity's footprint grows heavier, and as we continue to actively alter the Earth's delicate crust, Are we truly prepared for the unseen forces we might awaken? Thank you so much for joining me for this explainer. Keep your curiosity alive and always respect the raw power beneath your feet.